Okay, good. Let's begin. It's exactly 2:30, I guess. So before I start, I wanted to make few corrections actually that I missed it. Actually, there was some small error that I wanted to correct it, so that you don't go with some wrong expressions. When I said completeness, okay, yesterday. In quantum mechanics, completeness means you have to consider all 1 to n, okay, dqpi, okay. Then I forgot to put this summation over n is equal to 0 to infinity, okay. So this you need to take into account, okay. This is in some sense a completeness relation, okay. Here everything is summed, okay. This entire measure is all possible states, okay. So that summation is important. In deep inelastic scattering, this is precisely what you do. You count all the events, add them all, okay. And that is called inclusive. Whether you see a lepton in the final state, or a lambda variance in the final state, or cats and dogs, add all of them actually. And this is what it means. Okay, this is something one I forgot to add. This is summing over, inclusive, okay. And second one, actually, when the morning when I was talking about F2, okay, this is 2xbj times sum over all patterns. Okay, so when you sum, okay, you'll have to sum all the patterns that you can think of that exist in nature. So proton is not an exception actually. Proton also can have strange quark, bottom quark, top quark is not possible because it's too heavy, heavier than the proton. So anything that is lighter than proton mass, in principle you can have non-zero probability to find them inside the proton actually. Depends on the energy, okay? You will see more about it later on. So when I say this A means actually U quark, D quark, S quark, bottom quark, charm quark, anti-quarks like U bar, D bar, S bar, C bar, okay? So all these probabilities, all the species can actually be present in proton, and there is a finite probability. It's only the experiment will tell you whether what is the fraction that is dominating, which one is the dominant flavor, which one is the less dominant flavor, and so on and so forth. So whenever you have a sum over A, you'll have to add all of them actually. This is something that you should keep in mind. Very good. So now the question that I would like to ask is actually, very good, we have deep inelastic scattering that really explains the scaling that Bjorken actually sort of worked out, using some mathematics, and then experimentalists also wanted to check this, and then they did the check, and then they found the scaling was exact. Okay, at SLAC it was done. I have a plot actually, I'll show you at some point. Okay, there's a beautiful plot which shows how the f, the structure function, remains constant as you change q square to some value to some value. Okay, wide range of q square, the f2 was almost constant. It depended only on this Stirling variable x. Okay, that was a remarkable observation, also confirmation of very famous work by Bjorken. Okay, that led to this pattern model, and that led to better understanding of what proton is all about actually. Okay, so that's how this science progressed. Now the question is actually, well, this is one is actually based on some field theory, other one is based on the experiment. Now, is there a way that we can actually understand strong interaction physics from a stronger physics footing, actually, in the sense that can we have an equivalent of electrodynamics that explains all the phenomena related to electrodynamics, works. Okay, like you have a theory of quantum electrodynamics. Do you have any theory of strong interaction, which we can claim that it explains everything about strong interaction physics? Okay, and we'll have to see whether these experiments and also these theoretical developments ain't anything that we are actually looking for. Okay, so the answer to this question is actually this QCD. Okay, now we have a task in hand, a very well-defined task, namely anything if you think of as a theory for strong interaction, that theory should actually respect all those phenomena that we have seen. It should actually give you as a prediction. Okay, that theory should have this pattern model picture. Okay, otherwise it's not going to be used. Okay, that theory should behave exactly the way the Feynman thought about or Bjorken thought about. Okay, so you need a theory which explains. QED, of course, is not going to do, because QED, for example, at very high energies, as you know from field theory, it's strongly interacting. Okay, if you look at the strong theory of electrodynamics, and if you want to look at the behavior of QED at very high energies like here, it is going to be just opposite to what you see. You don't see weakly interacting point-like particles. Okay, it will be strongly interacting actually. This you might know. Okay, so fine structure constant grows as you increase the energy. You change the energy to very high energy. So you cannot use QED. Okay, you need an alternate theory. Okay, QED-like theory actually. QED-like theory is actually QCD. Okay, so you'll have to cross our fingers and wait until we calculate something that tells you that QCD behaves differently from the QED that we know. Okay, and it's exactly the same way that we expect actually, that it should have this picture where at high energies the particles in QCD should behave as if they are free, they are non-interacting. Okay, this is something that we have to actually write from the day one. You expect that QCD should describe. Let's see whether the theory that I'm going to discuss today is going to explain. So I hope the problem is clear to all of you. So if at all I can have a theory for strong interaction, that theory should have this peak coupling limit at very high energies. Okay, that's very important. Okay, so just a brief introduction to QCD, because I'm going to tell more about the role of QCD in the context of structure functions. Otherwise, the course will be incomplete. Okay, so the QCD is a theory of strong interaction. Just save time by not expanding them. The Lagrangian is actually psi bar I del slash. I think some of the earlier speakers had said. Okay, looks very much similar to QED. Only difference is the psi here is a column vector containing three types of fermions, come in three different colors actually. Color 1, color 2, and color 3, if you want to name it. Okay, and it transforms. Let me just go over slowly. And this d mu is actually what is called the covariant derivative, very similar to the covariant derivative you are familiar with in electrodynamics. The only difference is this covariant derivative contains not one photon, it contains 8 photons, and each photon is attached to a matrix. It's called Gell-Mann matrix. These are all 3 cross 3 matrices. Okay, so that is something. And they come in 8 in numbers, up to 8. Okay, and this TAs are generators of SU3 group. Okay, so this Lagrangian is constructed by demanding so it's called SU3 gauge invariance. Okay, so all that is fine. Okay, and this F mu nu here is defined by this equation. Okay, and this covariant derivative satisfies. I will also write down here. I'll save a lot of space because I'm going to talk about something on the impact of this QCD G F mu nu psi. Okay. So these are the famous ones, and this F mu nu here, if you expand, this will be del mu a mu nu minus del mu a mu minus IG, where a mu again is a mu a ta. So it is just a sum of 8 of them actually. So basically these are the things that you need to know for QCD. Okay, there is some covariant derivative sitting here, and there is this gauge field, which looks like this. Okay, very similar to QED1. The only difference is actually there is a commutator of mu nu. Commutator comes because this A is a matrix valued. Okay, this is fine. Okay, this Lagrangian is invariant, as I said in the beginning. Okay, so I'm not going to work out what is the transformation property. Let's assume, as we don't have time actually. So it is invariant under I'm not going to prove any of them. What are the invariances actually? And psi goes to psi, every value of x. I'll explain to you what this psi of x, where u of theta of x is element of SU3, okay? And this is nothing but, this is exponential of I theta of x. Okay, so T is a vector, okay? There are 8 components to this vector actually. Similarly, under psi goes to psi bar of x. This will be psi of x, u dagger of theta of x. Theta is the parameter, okay? So you can think of as a vector here, all of them containing. Okay. And this covariant derivative transforms like this. This is simple exercise, you can try yourself. Goes like this actually, u of theta of x this is how it transforms, and which translates to a mu prime is a mu u of theta of x in a very non-trivial way. It's called case transformation. Mathematicians call fiber transformation. Okay, so this is how it looks like. Under these transformations, this Lagrangian is invariant. Oh, that's a gauge invariance. Okay, and any gauge theory requires gauge fixing. Okay, otherwise, theory is ill-defined. So gauge fixing is part of the game, because otherwise it's ill-defined. Okay, so I need to introduce a gauge fixing term. This is L gauge fixing equal to minus 1 by 2 alpha. Gauge choice is yours. Okay, so I take my favorite choice, namely the Lorentz gauge, and any gauge fixing leads to ghost fields actually. Okay, ghost fields, GF. it's also GF, is it? And it's called Faddy-Popo-Ghost, FP. Okay, so it looks something like a del mu C bar A del mu C A plus G times FABC del mu C bar A mu B CC. Okay, so these are the terms. So you have a, you have a part of the Lagrangian which is, let me take some color one actually just to quote. So this is your original Lagrangian, very much like QED Lagrangian. The complexity lives in this A mu's. Okay, this is the gauge fixing. So this is the first part of the Lagrangian. This is the second part of the Lagrangian. So one comes from the gauge invariance, other comes from the gauge fixing. These are the two aspects. So any gauge theory that you write down, you should have these two sets actually. One looks very similar to QED, the other one which looks not like QED, but it gives you an additional piece because you are fixing the gauge. Very good. So far so good. Let's rush. So you get, as Abhay was mentioning, this Feynman rules will contain, a fermion line, okay, and then the gluon line, okay, and then the ghost line, okay, because there's a fermionic field, there's a gauge field, and then the C's are the ghost field actually. So there are three types of fields which allows to have three types of propagators in the theory. Other than propagators, this theory contains vortices. What are the vortices? This QED-like vortex like this, that gluon couples to fermions, and then gluons can also couple to gluon stem cells. Okay, that's simply because you have a triple gluon vertex if you expand F mu nu, F mu nu. So F mu nu, F mu nu allows you to have two A terms, A terms, and A, four A terms actually. So you will have a propagator, two gauge boson term, triple gluon vertex, four gluon vertex. Okay, so these are the ones that you can have actually. So these are the standard vertices actually. Now you can see that you have this ghost field coupled to gauge boson. So you have a very peculiar vertex, two, like this, ghost field coupled to this gluons. So this is something which is coming from the gauge fixing. So these are the only building blocks that you require to calculate anything in QCD. So these are nothing but building blocks for Feynman rules. Okay, that's all. So given this set of rules, I can actually perform computation either in perturbation theory or non-perturbatively, but I chose to work with perturbation theory. Okay, so the only parameter that I have here, two parameters, one is this mass, the other one is coupling constant. The coupling constant describes how all these vertices are parameterized. So that's how the couplings look like. If you look at it, 4 gluon will have G squared, 3 gluon will have GS, and 1 gluon will have GS. This will have GS, and so on and so forth. So now we have a way of organizing your Feynman diagrams by counting the number of vertices that you have in a given diagram actually. Okay, so this is one way of performing this. Okay, then a little bit about renormalization. Okay, I don't think anybody can teach field theory in half an hour. Okay, but I'll make an attempt. Okay, now this theory, of course, like QED, will be divergent. There will be ultraviolet divergence. You need to renormalize them. Why I need to do that actually? Because if I don't renormalize, I will get all kinds of divergences. Okay, so like QED, QCD also suffers from UV divergences. For example, if you calculate, diagram of this kind or diagram of this kind, okay, this is order GS square, this is also order GS square. These things will involve, divergent integrals. If loop momenta is k, then you can have 2 pi whole power 4. Okay, you have propagators like 1 by k square, k minus p whole square, and so on and so forth. These integrals diverge as k mu goes to plus or minus infinity. Okay, so they're called ultraviolet divergence, short distance divergences, very similar to QED ones actually. So you need to regularize them. So the remedy is actually, okay, how do I deal with this? You have to introduce what is called regularization. And then what is regularization means? Because these are all divergent quantities, okay, mathematicians will not be happy if you just proceed and compute things, which are divergent. So we need to actually regulate them, actually make sense out of it actually. So what is that actually? So you actually replace, okay, your integrals by another set of integrals which are well defined actually, okay, by introducing a regulator. So if you see an integral which is divergent, there's something called regularization. For example, if I see an integral x is equal to 0 to 1, it is divergent integral. Regularization means, what is meant by regularization? Regularization means either I can actually say that my lower limit is not 0, but at 0 plus delta. Okay, this is called regularization. Okay, and take the limit delta goes to 0 as an intermediate step. Okay, for example, in this kind of physics, we can actually go to dimensional regularization, which means take your space-time dimension to 4 plus epsilon, okay, where epsilon is small complex number. Okay, so by going to a very, 4 plus epsilon, where epsilon could be some negative value or positive value, depending on what kind of singularity that you see, you can regulate your integral. The reason why one chooses this dimensional regularization is because it's elegant, it's very easy to handle mathematically. Of course, the physics should not depend on what kind of regulator that you use. Okay, so I'm going to choose this as a regulator. So I will define wherever my space-time dimension d appears, I'll put d is equal to 4 plus epsilon. Okay, and you'll see all the divergences as poles in epsilon. So divergences show up as poles in epsilon. That means it looked like 1 by epsilon power some alpha. Alpha could be 1, 2, etc. Okay, so when epsilon goes to 0, that means if I take it to 4 dimension, it will diverge. So it's called regularization. Okay, what is renormalization? This is the first step that you do. Okay, step number one is actually regularization. Step number 2 is renormalization. Okay, what is renormalization? Renormalization, again, I'm going to tell you in very short terms. Okay, what is renormalization? Renormalization is the following. So you have a set of fields psi bar, a mu, coupling constant gs, and mass m, and so on and so forth. Okay, so all you do is actually you replace or redefine, okay? It's also called redefinition. Okay? So you write every psi field as some z times, okay, at some arbitrary scale mu r times some psi r. Just definition, rescaling by some factor z. Okay, I choose this z in such a way that it is a function of epsilon because I work in a regularized theory. Okay, so I can choose exactly like this psi bar. I can put off here, psi here, just to distinguish because I have many of them. Okay, so you do this replacement. Okay, psi bar r of x, and so on and so forth. Okay, for all the fields, A mu's, ghost fields, etc. And you should also do same thing for your coupling constant or your mass. So mass is also related to Zm mu r epsilon, okay, times m of mr. Okay, so you can also do for coupling constant. So I'm reserving a special place for coupling constant. So Gs, that coupling constant that you look at in your other part of the screen, is actually in d dimension is dimension full. Okay, because if you rescale all the fields and look at the action is in dimensionless, you'll find that Gs is dimension full. So all you need to do is actually you should write it in terms of a dimensionless parameter. I'll tell you what this exactly. This is mu power epsilon by 2. Okay, and this is rescaled to z g power of, okay, times mu r epsilon g s r mu r. Okay, this is how it is defined actually. So unlike other parameters where you have the z factor which is sitting here, which rescales your couplings and fields, you need to actually rescale your coupling constant also in a very peculiar way actually. Okay, because the coupling constant in 4 dimension is dimensionless. However, in n dimension, it is a dimension full in n dimension. Okay, so it is a dimension full, you need to rescale them actually. So this is how the coupling constant would look like actually if I rescale them actually. Okay, now this is the first step, redefining them. Okay, this is not sufficient. Okay, so renormalization means imposing certain conditions on your Green's functions. So if I consider the demand is actually that you impose, okay, of any Green's function that you compute, any arbitrary Green function that you compute in your theory has to be finite. Okay, okay, this will fix all your renormalization constants. All your renormalization constant Zi of mu r epsilon terms. Okay, so by demanding this, so this is a very crucial point. So I need to actually regularize all my integrals or all my Green's functions. And second step is actually redefine all of them by this way. Third step is actually impose a condition that all your Green's functions written in terms of renormalized fields have to be finite. Okay, if you do these 3 steps, like when you go to temple, you do this, this. Okay, all your power will be gone. Like that, if you do these 3 steps, then you will find that all the z's will be fixed, okay, once and for all. Okay, given that you can compute any Green's functions in the theory, you will find that it will be finite actually. Okay, that's what this renormalization procedure means. Okay, I hope this is clear. Yeah. I don't know what z's are, no? Z, I've just put it as the overall factors actually. How will you fix Z actually? Z is unknown. So I write psi equal to Z times psi. A mu is equal to Z into A mu. I need to fix all the Z's actually. So I need to impose some condition on Green's function. Only it's, very simple-minded condition is actually any Green's function that I compute, that has to be finite if I compute it using this renormalized fields. That fixes all my renormalization constants. Once you fix renormalization constants, you can compute anything you like. Okay, so that's the program. Okay, there are 3 steps. I've explained all 3 steps. Okay, in private, maybe I can discuss with you more on this because field theory cannot be taught in half an hour time, but I tried my best actually. Okay, now why I did this exercise? I did this exercise because I wanted to bring you to very important thing, namely how the coupling constant behaves actually. As I said, all the z's can be fixed. Let me also write down the most general form of z actually, how it would look like. Okay, so all the z's in dimensional regularization would look something like this actually. So my Lagrangian, if I do this renormalization, okay, originally it had contained psi bar, blah, 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 okay, GS would look something like L, okay, psi bar, okay. If I do all of them, then it look, there will be Z factors, U R, let's say I, and explicit dependence on mu R, okay. So all of them will be like this. It will have a completely different looking structure, and I rewrite this as L, which has the form which is very similar to what I had earlier. The only thing is I'm going to strip off this Z dependent part separately and call that as counter term actually. So this will be psi R, psi bar R, blah blah blah, Z I mu R. Okay, these are the counter terms. So this will generate set of Feynman rules. Okay, this will also give us new set of Feynman rules containing the Z factors. Okay, these are the things. So Z in generically would look something like this. Zi of mu R of epsilon would look something like AS. I'll write down what this means actually. AS times Z1 minus 1 epsilon, okay, plus AS square mu R square into Z minus 2 epsilon square, Z1 1, this is 2 by epsilon, blah 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 blah. This is how it would look like, where this AS of mu R, for convenience, I'm writing it as GS of mu R whole square by 16 pi square. Okay, so this is typically the structure that you get if you perform your perturbative calculations. Okay, so every Zi actually, maybe I'll put this I here, this I here, okay, some comma, comma, comma. So all of them would look like this actually. The first non-trivial order, it will have 1 by epsilon, and the second non-trivial order, it will have 1 by epsilon square and 1 by epsilon, and so on and so forth actually. So it just goes on like this actually. That is the structure that you get. Okay. Now, given that, what is that you will get actually? Given that, sorry? All the renormalization in general, I can write it like this actually. Okay. So generically, they do look like this actually. So the original Lagrangian expressed in terms of these new fields, psi r and AR and etc., now will contain the Z factors. Those Z factors are singular now. Okay. And as I said, Z factors are known. The values are known because I demanded that all my Green's functions in the theory are finite. If you demand something is finite, you can fix all the constants. So you are putting some condition by hand. Okay. The condition is actually, if you compute any Green's function in the theory, QCD, using this renormalized fields, I should get finite result. That's only demand. Very, very simple demand actually you can make. Otherwise, you cannot fix any Z factors. Okay, and this procedure actually, okay, provides you a Lagrangian, which is actually giving you finite result. If you calculate any cross section that you like in QCD, you'll get finite result. That is what is guaranteed here actually. Okay, this entire program is called renormalization. This is done in QED, electroweak theory, and also in strong interaction theories. Up to this is clear to everybody? So this entire thing that I discussed, can we put it in this page? Given this form of the Lagrangian, you can compute anything you like actually. Okay, now why I did this exercise? Okay, I'm not interested in making you to work and calculate something which is for QCD. Okay, but I wanted to show you something very interesting happens in this theory. Okay, if I just look at only the coupling constant. Okay, so coupling constant, as I said, is related to that form, related to the Z factor in this following way. I written down here actually. So if you want, I can highlight this and take it to that place. Okay, so let me take it to that place and do a little bit of modification and show that it has a very beautiful, behavior. Okay, let's start with this GS at power mu power epsilon by 2 is, I said, Z coupling constant GS power of, okay, this is function of mu r epsilon times GS of mu r square by mu r power epsilon by 2. Okay. Now square on both sides. So G at square by 16 pi square, I call AS at. Okay. Similarly, GS square by 16 pi square, I call AS without hat. If that is the case, you can write it as AS at divided by mu square power epsilon by 2 equal to Z GS, okay, mu r epsilon, okay. Then this is AS of mu r square power epsilon by 2, okay. This is very, very straightforward actually. Is this clear to everybody? So bare coupling constant is AS at is related to renormalized coupling constant. And Z, I know what is the structure of Z. Okay. So now take log on both sides. Log on left hand side okay, log of ZGS plus log of AS of mu r square minus epsilon by 2 log of mu r square. This is also straightforward. Take the log of this on both sides. You get this equation. Now you do this, take the derivative with respect to mu r square. First derivative on this. What is the first derivative of the left hand side? If I differentiate with respect to mu r square, this is AS at, this is mu square, differentiating with respect to mu r, it will be 0. So simple, no? So this is 0 equal to derivative with respect to mu r square, d by d mu r square, log of ZAS, okay? And this one, mu r square, okay, d log of AS of mu r square divided by d mu r square. What about this? This is just minus epsilon by 2, okay? So this is some relation that you get relating how coupling constant changes with respect to scale mu r with, and if you change the renormalization constant with respect to mu r, okay? Is this clear to all of you? So it is a first order differential equation that you get from this kind of a renormalization procedure, okay? It tells you how coupling constant changes if you change this, okay? Any change in Z will be compensated by this change in the coupling constant. That's what it means. The sum has to be 0, okay? So let's see what this consequence of this result, okay? Let me just rub this part. What does this tell you? Okay, so I'll just bring here and there back. So you can write it as mu r square TAS of d mu r square equal to this is epsilon by 2 did I do it correctly actually? So this I get epsilon here actually, and just give me a moment. So this is epsilon actually for me, because why I did this actually, this is square by epsilon by 2. Okay, so let me put actually and proceed actually. So this is correct what I'm doing. So this is minus, minus, minus. Okay, now let us put this, calculate this quantity with respect to AS of mu r square here, okay? So I'm just proceeding, mu r square, this is epsilon by 2, okay, minus mu r square, d by d mu r square, ln of, this will be AS, okay, and then this entire thing will be multiplied by AS. Okay, so all I did is actually I just brought this derivative of this d a by d mu r to the left hand side, or kept this but and move this part to the right hand side. So this is epsilon by 2 plus this and this. Okay, everything is clear. So I'm keeping this epsilon intact actually. Epsilon is actually deviation from 4 dimensions. Okay, now I need to compute this quantity. I need to compute this quantity. What is this quantity? D mu r square by dz by d mu r square, which is, let's keep only the first order term and drop all the other terms. So it is just simply, dAs by d mu r square times, there is a 1 by epsilon here, and then z1 of -1. Okay, this is what we get actually, some constant times this. Now this is same as the left hand side. Okay, now if I iteratively put it back here, this will be, first term will be proportional to epsilon by 2 into As, and this will be 1 by epsilon times z1 1. So this epsilon cancels, so you get As by 2 z minus 1 1. This is what you get actually. Okay, so up to the order As square up to the order As square, you get a term which is like this actually. So this equation now becomes mu r square dAs by d mu r square equal to epsilon by 2 As plus, this is minus term, As z1 minus 1 by 2 up to order As square. Okay, so this is your equation. It's finite as epsilon goes to 0. Okay, if I take epsilon goes to 0, it is finite. Okay, even though this renormalization constants and coupling constant to start with are all divergent quantity, you find that the coupling constant, the evolution of the coupling constant actually is finite. Okay, let me make it, and so I can set epsilon is equal to 0 and drop this part. Okay, so I forgot to put one more term. There is overall As here, so this becomes As square. So this is As cube. Okay, so this quantity is finite. All I need is actually, if I want to solve this equation, all I need is actually this renormalization constant at one loop order actually. That means I need to compute this renormalization constant. That I can do it by fixing one of the Green's functions. Okay, if I do this, the answer that I get is really startling. It is, you'll find that this answer to this is d by d mu r square As of mu r square in the limit epsilon goes to 0 is simply minus As square. Okay, some explicit computation will tell you that 11 by 3 Ca minus 2 by 3 and F. Okay, plus order As cube, etc. This is what you get actually. So this one, this factor where Ca is n square minus 1 by 2n. For QCD it is 3 by 4. This is 3 by 4. And CF, this is CF, this is CA is n equal to 3. Okay. Now we put this number back, you get something greater than 0, this quantity, which is, okay. Sorry? 4 by 3, okay, very good. Is that okay? So you have something like this actually. So this is what is called the renormalization group equation for coupling constant. This is called renormalization group equation for strong coupling constant. Okay, so far in 45 minutes, I only managed to show that QCD contains a strong coupling constant, and QCD is a field theory, hence it will have divergences, particularly UV divergences. And in the process of renormalizing, you will get renormalized coupling constant. And this renormalized coupling constant, if you call by AS, that coupling constant satisfies differential equation of this kind. Okay? And if you explicitly work out this renormalization constant for the coupling, you will find that it turns out to be 11 minus whatever, 2 by 3 NF. Okay, because CA is equal to 3, this is simply minus AS square times 11 minus 2 by 3 NF. Okay, so what is 11 minus 2 by 3 NF actually? Suppose if you have 5 flavors in the theory, okay, 11 minus 10 by 3. Okay, so it is greater than 0, and this entire right hand side will be less than 0. Correct? Okay. So this is the equation that is going to tell you whether your theory is something that we are looking for. The theory that can tell you at high energies, it looks as if it's completely free. Okay, so that was the starting point in my in today's this afternoon's discussion, that I was looking for a theory, okay, a sensible theory. That theory should have this following property, namely, if I go to very, very high energies, that theory should have particle and field content that are completely free. They do not know each other. One gluon should not know the existence of other gluon. A quark should not know the existence of antiquark or other quarks. If there is a ghost field, the ghost should not understand there exist gauge bosons. Okay, when will this happen actually? Original Lagrangian contains couplings of all of them actually. Okay, only if the coupling becomes 0, then it can happen actually. Okay, now it's a very crucial moment to check whether this coupling constant at a high energy is going to grow or going to vanish actually. If it grows, then I'll have to say, sorry, I made a blunder of choosing this theory to describe strong interaction physics. If this coupling is going to sort of fall off to 0 at very high energies, then I would take this theory a little seriously. Okay, that's not sufficient, but at least necessary condition. Okay, so we'll have to check whether this coupling constant is indeed showing that behavior. Okay, for that we need to solve this equation. That's why I worked out all this algebra, that if you do renormalization correctly, then you will end up with this differential equation. And this differential equation is going to tell you whether your theory is going to be useful for your physics of strong interaction. Okay, let's solve this actually. This is a very elementary exercise. You don't really need a lot of techniques to solve, because this is very easy to solve. First order differential equation. Let me solve this, okay, in one line and write down the solution. Okay, so dAs by As is simply, I keep only to order, A square. This is As square. Okay, correct? Is this? Let's call this quantity beta naught. Okay, so let's say minus beta naught times d mu r square by d mu r square. Okay, so integrating on both sides, let's say you integrate from, let's say, mu 0 square to As of q square. Okay, sorry, Sorry? d mu r square by d mu r square. Very good. Okay, so you integrate this. This will be 1 by as of mu 0 square minus 1 by as of q square equal to minus beta naught times log of q square by mu r, mu 0 square. Okay, so as of q square will be 1 by 1 plus as of mu 0 square beta 0 times log of q square over mu 0 square times as of mu 0 square. Okay. So this is how it looks like the solution. Okay, I dropped terms of order a square. Okay. Now it's very easy to actually tell you that if I increase the scale q square to very large value, this log is going to grow fast to make this term to 0, right? If q square is very, very large, there's some number divided by very large number is going to go to 0, okay? So this has this nice behavior as a q square going to infinity, it vanishes to 0, okay? This property is called asymptotic freedom, okay? Now I can say, hooray, actually, that we have got a theory which is exactly the property that we are looking for actually. This is called asymptotic freedom. Okay, so coupling constant goes to 0 at high energies or weak. Okay, so this is what we think is the right theory for strong interaction, because deep inelastic scattering or a Drell-Yan process that we discussed, we considered an energy region where the probe, this lepton that actually scatters off the proton, or in the Drell-Yan case, it's a pair of leptons, the probe actually sees the proton at very, very high energies, okay? It means very, very short distances. And in short distances, this particular theory behaves as if it's a free theory, okay, weakly interacting. So if there is a candidate to describe partons, they have to be these fermions in this theory, okay, which have got color, they come in 3 numbers, 3 colors, and the gauge fields, they come in 8. All that property should be there actually. So the proton that we have been studying, okay, from Feynman's perspective and also from the experimental observation, okay, they all will nicely fit into this nice theory called QCD, which exactly has the property that we are looking for actually. Okay, so this property is called asymptotic freedom. Of course, this theory also should tell you that at low energies, the coupling constant has to be very, very strong, and also bring all the these quarks, these fermions are called quarks and antiquarks. They should actually bind them together and form a proton. Okay. In fact, Abhay mentioned that QCD explains why proton mass is 900 and whatever number. Okay. It's simply because if you try to compute on lattice using QCD, the mass of the proton, which is possible to calculate, and the number really turns out to be what you mentioned actually, that what experimentalists find. Okay, so this interaction that I'm talking about, which is responsible for asymptotic, free parton picture, is also responsible. The same coupling is also responsible at low energies to describe the proton and also confirm that the mass comes from this interaction, this QCD interactions. The strength of the coupling constant is so large, and it gives you, the mass that we need to actually verify. Okay, so this theory has two aspects. One, at high energies, it explains high energy scattering experiments. At low energy, it explains properties of baryons, okay, and mesons very successfully. Okay, so we use two different frameworks. One is called the perturbation theory to describe, this kind of scattering processes, and lattice case theory to describe, the low energy properties actually. So this is what I thought I would tell you in 1 hour. I completed that actually. So do you have any questions? I hope I convinced you that QCD is the right theory to describe. Okay, you need to do a lot of work actually to come up this. But I tried, to illustrate in simple terms. Okay, renormalization itself is a one semester course. Okay, so I cannot justify that I have done this successfully. Okay, but it is just gives you a flavor of what's going on actually. Okay, if you go back and read, if you have not done renormalization, this will help you. Okay, good. Is that okay? So we'll have a break and then come back. Okay. Yeah. Lattice, yeah. There is no other, satisfactory methods actually, because lattice is really field theoretic approach, because you put QCD Lagrangian on the lattice. Okay, lattice provides a regulator actually. Like, dimensional regularization provides regulator to calculate quantities in perturbation theory. Lattice provides kind of a regulator actually, because these divergences are going to be there anyway. So you need lattice to regulate this. So it is possible actually. I think there is a famous paper by some American group and Chinese group. They actually calculated this quantity, proton mass. It's one of the successes of QCD, I would say. So, any other questions? That's all? Oh, sorry. Very recently, 1.5 years or 2 years before, actually.